Here we go. Taylor polynomials. Yes?
That's a weird name for his time.
He was an accomplished musician and painter, did research in a variety of areas, but is most famous for his development of ideas regarding infinite series. All right. Don't write it down.
No, but quick question.
Yeah.
How does like someone become a musician and painter and then all of a sudden, oh yeah, I'll do something with like infinite series?
Okay, so kind of like how you really like math and computers and all that stuff, but you probably also like spend your time like playing computer games, right? Rubik's Cubes. Okay, it's like a hobby, right? Being a musician, a painter is like a hobby. They just don't have like Rubik's Cubes and video games and TV and all that stuff to get themselves distracted.
There's also like the Roman era, so you're looking at a bunch of people developing.
Say that in the fine arts department, people are like, what?
That is true. That is true.
That's why that happens.
Now, what we are going to do today, who agrees that polynomials are the easiest functions to work with?
Most of the time.
Okay? We can graph polynomials without our calculator. We can find polynomial zeros without our calculator. Polynomials, we know the ending behavior without having to graph them. We know a lot about polynomials without graphing them. Okay? Taking derivatives of polynomials, easy. Taking antiderivatives of polynomials, easy. Evaluating polynomials, easy. Okay? So, what if we wanted to approximate a graph at a particular place that's not polynomial, but we wanted to use a polynomial because they're easier to work with? Just watch what happens. Okay? Just watch what happens. Okay? So you can sit back, relax. Okay. So we want our polynomial at 0 and our function at 0 to be the same. And we want the first derivative to be the same. And we want the second derivative to be the same. And we want the third derivative to be the same. And we want the fourth derivative to be the same. Right? If we're going to use them to be equal there, those would all need to be the same. So here's our polynomial that we're going to use to model the natural log of x plus 1 at 0. So first of all, let's consider our function, natural log of x plus 1. What is the value at 0? 0? Okay. Okay. All right. So on our polynomial, p of 0 is just that this a sub 0 term, right? If we plug in 0, we're only left with this, which means if we want these to be equal, well then a sub 0 is 0. Cool. Next, what's the derivative of our function? 1 over x plus 1. Cool. Evaluated at 0. It's 1. Okay. Our polynomial, the derivative would be, that goes away, a sub 1 plus 2 coefficient times x plus 3 coefficient x squared plus 4 coefficient x cubed. You agree? All right. We evaluate that at 0, and we're left with that coefficient a sub 1. A sub 1 needs to be 1. Okay? Second derivative. Try that again.
Wait, yeah. Negative 1 over 1 plus x squared by quantity.
Negative 1 over that quantity squared. Evaluated at 0. -1. Polynomial second derivative. 2a sub 2 plus 6a sub 3x plus 12a sub 4x squared. When we evaluate that at 0, we're left with 2a sub 2. That has to equal the -1 if we want these two to be the same at the second derivative. Therefore, a sub 2 is -1/2. Interesting. What? Are you noticing a pattern? Is that what you're doing? Okay. All right, so I kept this up here for us. Third derivative. 2 over 1 plus x cubed. Okay. Evaluated at 0. 2. Okay. Third derivative of our polynomial. 6a sub 3 plus 24a sub 4x. Oh, what's going to happen? 2 to 6. I'm going to keep it as 2/6, and you'll see why here in a moment. And in the fourth derivative, well, remember, once we get past 3 tick marks, that's enough. We write numbers. We're gonna get up until like 7, 8. No. So the fourth derivative at 0 is -6. The fourth derivative of our polynomial is 24a sub 4. I hope you see a pattern. And if we want those two to be equal, then a sub 4 is -6 over 24.
Whoa.
Got it. Okay, what we have is, there's our polynomial. Which, yes, we could reduce to this, but I'm going to leave it like that for now. Now, this is what I want to do. I'm going to put this into Desmos, okay? So our first function is the natural log of, is it x plus 1? Okay, and I'm going to zoom in. Okay, are you ready? Are you ready for this awesomeness? Okay, y equals 0. That was our first term. Okay, that's not helpful. Plus x. Well, we get closer. Minus 1/2 x squared. See how it fits a little bit tighter? Okay. Plus 2/6 x cubed. Fits a little bit tighter. Minus 6/24 x to the 4th. What do you think is going to happen as we keep going? Okay. Okay, so we can use polynomials to approximate our curve around a particular point. Now, this only works for x equals 0. Okay, but at x equals 0, look at how close those curves are to each other. Okay. Okay. Now, oh, sorry. So our polynomial was this. Do you notice how each of these numbers, that was the derivative? Are you guys noticing that? Yeah? Okay, what are these numbers? 2, 6, and 24. It's a factorial. More specifically, 2 is 2 factorial. 6 is 3 factorial. 24 is 4 factorial. If we use this to approximate polynomials, this, right? This pattern is going to occur no matter what the original function was. On Capitol Hill. All right. So, we are going to talk about Taylor polynomials. Okay. There's also such a thing called a Maclaurin polynomial, which is a special type of Taylor polynomial. Here is a Maclaurin polynomial. Maclaurin is the specific type when we generate around x equals 0. Taylor is when we are centered around a different value. Have a type of where? Polynomial. Polynomial. Yeah, male to be male. Anyone else catch that besides him? Nope. Nope. Yeah.
So we're not needing money? So we need this. Yeah.
I think but because it's using money, but you just didn't.
Yeah.
What are you thinking about?
I got it.
Okay. Yeah, I'm using it, but I don't know. So, is it like official?
Yeah.
Yeah.
I didn't hear about it until after I said this. They were like, natural merit, right? I'm like, I don't know. What's else like?
Yeah, do you guys all know?
Oh, you got the thing?
Grayson and Sammy got the thing.
The thing.
Well, we got the finalist thing, but there's still another level.
There's still another level?
Yeah, I mean, we get the scholarships at this
Yeah.
point, but like there's.
Okay. But this is like. the
Yeah,
level
this is
that-
like the one that actually
This is
matters.
the level.
Yeah.
All right, so congratulations. That's so exciting.
I have a question about Friday night.
Yes.
So, can I like maybe just like I can hang out in the rafters, like to a rope or something?
Yeah. They have that too.
Take them out. I can get a walkie maybe.
Yeah.
Okay, so this is what's going to happen. Do we all have written down what we need to write down?
And then me and Jake can have some walkies together.
If we bring our own.
Yeah. Over.
You gotta make a noise with it. Over. Steven Silverman? Anybody? No? No? Cool. All right, so when we had the function
Maybe she gets a cups with a string.
natural log of x plus 1, okay, this is what you're going to have to do. You're gonna have to evaluate f of 0 to be 0. Okay? Well, okay, so what I showed you was us developing the Taylor polynomial
Right.
before you knew what a Taylor polynomial was. So now I'm saying, okay, if this is your function and we're centering at 0, then you would first evaluate the function. Then you would find the derivative and evaluate the derivative. Okay? Oops, pardon. I don't know what that's the next one. And you would find the second derivative and evaluate it. The third derivative. And evaluate it. And the fourth derivative. And evaluate it. For the fourth degree, in this case, Maclaurin polynomial, you would write that our function is approximately this polynomial, which is f of 0 over 1 factorial times 1, well, that's 0, right? Plus the first derivative over 1 factorial times x to the first, plus the second derivative over 2 factorial times x squared, plus the third derivative over 3 factorial times x cubed, plus the fourth derivative over 4 factorial times x to the fourth. You need to remember a pattern. If you can take derivatives, evaluate them, and remember this pattern, you can make any Taylor polynomial that you want. That is all we're doing. Right?
Basically, could you make a graph if you carried it out to that extent?
Well,
On,
We're gonna do the particular of that?
we are going to work with Taylor series.
We're gonna do the conversion.
Yes, yes.
some of them are gonna have 0, like, after a certain point. This one won't, because.
I do want to point out that if we are centered at a non-zero number, we're evaluating at that value, and instead of x, we have x minus a. We are going to write a Maclaurin polynomial here. Okay, so we're centered at 0 if it's Maclaurin. All right. So, our function is cosine of x. Evaluated at 0.
1.
Okay. Jake, derivative. Evaluated at 0. Isaac, evaluated at 0. Okay. Nick, second derivative. Peter, evaluated at 0. Third derivative, Sammy. Evaluated at 0. Alex?
0.
Austin, fourth derivative?
I got 1.
Well, what is the fourth derivative?
Fourth derivative cosine.
Grayson, evaluated at 0? Are you seeing a pattern?
Yes.
What's going to happen next?
Be negative sin x and 0x.
It's going to be 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, right? Right? It's going to keep going. Okay.
Backwards.
So, our polynomial, P for polynomial, 1, because that's the function evaluated at 0, plus 0x plus second derivative over 2 factorial times x squared plus 0 over 3 factorial plus 1 over 4 factorial x to the 4th. And I bet we could even predict what the next non-zero term would be. Negative 1, 6 factorial x to the 6th. What would the next one be? Okay, this is actually one that we will talk about here again soon. When we actually get into Taylor series and Maclaurin series, this is a series that I want you to remember. Okay. But for right now, we're just going to work on constructing it. Right? So, let me just show you a graphic here. Okay, so here is cosine of x. Here's 1. Lame. 1 minus x squared over 2. Next. 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 Next.
No way.
Oh.
No way.
Isn't that sweet? That's sweet. Okay. Now let's do this one.
That's also something that said rather than start from scratch.
Huh?
You know, learn shortcuts.
We will have some shortcuts later. What? Yep. And let's go ahead and create a 5th degree. If we want a 5th degree Taylor polynomial, how many derivatives do we need?
4.
Well, we would need up to the 5th derivative. Okay? So, our function at pi over 2. Well, here, let's see this. Our function is cosine of x, evaluated at pi over 2. 0. Our derivative is negative sine of x, evaluated at pi over 2. Our second derivative would then be negative cosine of x, evaluated at pi over 2. These are kind of boring, right? Third derivative would be positive sine x, evaluated at pi over 2. Aren't you glad? Aren't you glad that You don't have to write like 4 and 5 tick marks for these next derivatives. Fourth derivative. Cosine of x evaluated gives us 0. And our fifth derivative. Negative sine of x evaluated negative what? This. I don't want to sit there and count your tick marks. So our polynomial is, oh, why does this keep happening? 0
What if I just put numbers the same?
plus negative 1 times x plus 0x squared plus 1 over 3 factorial. Oh, Mrs. Holman. It's not x, isn't it? It's x minus pi over 2.
Is that the negative on the outside?
Yes. For this negative 1 right here.
Right.
We don't have an x squared term, but then we're going to have 1 over 3 factorial x minus pi over 2 cubed. We don't have a 4th degree term, but then our 5th degree term would be negative 1 over 5 factorial x minus pi over 2 to the 5th. Now, here there's no reducing that you need to do. You can leave them as 1 over 3 factorial, 1 over 5 factorial, or you can write them as 1 over 6 and 1 over 720. Yes, 720? Sure. Okay. It is up to you whether you want to reduce or not. I'm not going to throw a big fit about it. Okay. Like over, oh, this is going to take forever to get to, isn't it? Like over here, like if you reduce that to be 1/3 and 1/4, I wouldn't care. That would be fine. Okay? Now, one more thing I want to talk to you about, and then I'm going to make you do a couple problems before you leave. Oh, I really had all of that? Oh, I didn't think I had all that. Okay. Let's talk about the difference between number of terms or degree. If we talk about this function right here, this has 3 terms. But it's a 4th order Taylor polynomial because it's 4th degree. Okay? If I say 4th order Taylor polynomial, you need to take it out to 4 derivatives. If I say 4th degree polynomial, okay, same thing there. But since there is a term or 2 that is 0, instead of 5 terms, we really have 3. One minus x squared over 2 factorial, we could say that it is a 3rd order polynomial, but it's degree 2. So those aren't always going to go hand in hand because you could have a 0 term. You know what I mean? Okay. So it is 3:12. I want you to get your book out. I need you to do at least 1 problem, but I think you can get 2 problems done before you leave. Challenge.
Did we run out of that book subscription? I think we did.
Did you? I don't know. You never let me know. Now let me pause this and then